studies. My co-authors on the study are Reick, Houghton, and House. And together with them, I looked at a flux that most of you will know as either the net land use change flux, or the net land use flux, or simply land use emissions. And this net land use flux is the most uncertain component of the global carbon budget. But the good news of this talk is that it easily reduces uncertainty by a factor of 2 or more. Why were we interested in the net land use flux anyway? Looking at the most recent estimates of the human impact on the global carbon budget, we realized that the net land use flux accounts for about 10% of the anthropogenic CO2 emissions per year. But it is also important for the terrestrial sink, because from observations we can derive only the net exchange between land and atmosphere. And then we need models to simulate the net land use flux. And then subtracting these two fluxes from each other, we get the terrestrial sink as a residual term. And therefore, understanding the residual terrestrial sink totally depends on understanding the net land use flux. However, the net land use flux is associated with an uncertainty that is almost an order of magnitude large. A few previous studies have tried to find the key reasons for this large uncertainty. Most recently, Houghton led a model comparison study where we compiled 13 different published estimates of the net land use flux and identified 3 key reasons for differences. The first was that the different modeling studies assume different rates of deforestation. The models simulate different carbon densities or use inventories. And also they differ in terms of inclusiveness of management practices. Some, so going partly towards what Sebastian just outlined, some of them account for wood harvest, but others don't, for example. And down here, these 13 studies compiled, but this is just a subset of what's out in the literature. And these reasons explain much of this model spread. However, there's another key reason for uncertainties that has been largely unrecognized. And this is that there's large differences in the estimates of the net land use flux simply because we define it in different ways in different studies. This is what I mean by terminology. And these definitions largely depend on the model setup. Although definitions differ a lot, what is common to almost all of those studies is that they derive the net land use flux as a difference of 2 model simulations. The one is a simulation accounting for land use, and the other one is imitating the world if there had been not such a human activity present. And then we subtract the net land atmosphere flux of this with land use simulation and the without land use reference simulation to get the net land use flux. So doing these 2 simulations, there's a lot of different choices you have to make in terms of your type of model and the setup of these simulations. And the aim of our study was to provide a framework to partition the net land use flux in a way that we can then compose it together again to match what previous studies have done in their very different definitions. And this is the first part of my talk, this modeling, this flux partitioning framework. Then I will tell you what are really those important choices and setup you have to make and how they matter, show you what definitions have been used in the published literature, and finally talk about what this really means for our understanding of the global carbon budget. So to start out, we tried to break down the net land use flux into as many component fluxes that are needed that we can then explain consistently all published definitions of the net land use flux. I know that frameworks can sometimes be a bit boring, but to understand this is really important for the rest of my talk, and it's not going to take all that long, and it's actually pretty straightforward. But down here you have a status bar to follow where we are in our framework explanation. So, very simple. We've got a certain year with a given land cover. We've got some natural land, for example, forest, and we've got some managed land, for example, an agricultural field. But now land use change happens. So we transform part of the natural land to managed land. And what happens is, well, there are direct effects of land use change. Direct meaning they're referring to a real change in vegetation distribution from one type to the other. And what happens is there are instantaneous emissions occurring, for example, when we burn the forest. And that's those legacy fluxes, for example, due to the slow adjustment of the soil carbon pools. And the little subscript U here just means that we're not accounting for any changes in environmental conditions at this stage. However, these changes in environmental conditions obviously occur because these emissions go straight to the atmosphere and they change climate and the atmospheric CO2 concentration. And this leads to indirect effects on human activity. And this is indicated by these delta E terms. E stands for changes due to stands for fluxes due to changes in environmental conditions, and they may be caused by the environmental changes due to land use change. This is the delta L. However, they may also be caused by other human activities such as fossil fuel burning, which can also be prescribed in the simulations. And what you may have noticed is that our vegetation here is regrowing. This is historically because CO2 fertilization has been very strong and increased the standing biomass in the soil carbon stocks, and even more so when they account for fossil fuel CO2. Now, why this is important is because when we now clear again a patch of natural land, we're going to increase our emissions because there has been more standing biomass. And these are combined effects of direct and indirect effects of land use change. Well, this implicitly was our with land use simulation. But as I said before, we need a reference simulation not accounting for the land use change. And the only difference really is that the area being transformed from natural to managed land would be left at its natural state. But because this forest doesn't actually exist, we call it potential forest, because it actually the land is managed currently, but we could imagine under our model simulation it would still be the natural forest. And again, here also those delta E fluxes occur. Now let us sort these fluxes, because it's a whole lot of individual fluxes. Let's sort them by environmental conditions, being undisturbed, altered by land use emissions or by fossil fuel, and sort them by type of land, managed or natural in the with land use simulation. There's 10 fluxes. There's 10 fluxes that come over from here to there. And with the without land use simulation, that has 4 fluxes, it has the potential vegetation, natural vegetation. And we can bring them all together. I use brackets here for the potential vegetation because these fluxes will always be subtracted in your with minus without land use simulation setup. And you see there's 12 potential fluxes in our framework that you can quantify when you simulate the net land use flux. And as I'm going to show you later, published studies have used as little as 2 of these fluxes and as many as 10 of them in their definitions. So we're done with the framework. What do we do with it? Well, we can use it to identify those key choices in model setup that lead to very different processes being included or excluded in our definition. There's 3 important choices. The first one refers to the land use feedback. When you perform an offline simulation, as many GV2M dynamic low vegetation models do, you prescribe exactly the same environmental conditions to both your with and without land use simulation. For example, you use observed climate, which would then implicitly account for disturbances due to land use change and fossil fuel burning. However, these delta E fluxes induced by these changes, they really cancel because you prescribe the same environmental conditions in both simulations, they cancel out. But this is not true if you use a coupled Earth system model setup, because the without land use simulation will not see this increase in CO2 due to land use emissions. And therefore, these fluxes will be included in the net land use flux estimates of an Earth system model setup. That was number 1. Number 2 is the loss of additional sink capacity, also known as land use amplifier effect or replace sources and sinks. We said that when we have increases in atmospheric CO2 over time, the biomass, the standing biomass on land increases, and so there's an additional sink we have created by upchanging the atmospheric CO2 concentration. But obviously, when we clear this forest, this additional sink is lost. And this happens only when we account for transient changes in environmental conditions. If you just assume that your environmental conditions stay constant over time at a pre-industrial level or at present-day level constantly, there's no additional sink increasing over time, and therefore there's no loss of this effect. So this is the key difference if you have transient versus static environmental conditions prescribed to yourself. And number 3 is whether you perform a reference simulation or not. We said it's crucially important to do so, but a few studies don't do it. And what they then usually report is only the instantaneous flux to the atmosphere. What is not accounted for is the delayed emissions and the regrowth on abandoned agricultural land. Forests can be covered, but you can only separate them when you know via the reference simulation your other carbon fluxes. So these were the important model setup choices you have to make. And now we went through all the published studies in literature about 2,000 have global estimates of the net land use flux, identified their types of model used, the model setup, and then knew which of these effects they included or excluded, and found what definitions really existed in the literature so far. And this is the complete picture. And if you quickly count, you will realize there's at least 9 different definitions that have been used in the past. This may not sound that much when, from a mathematical perspective, you're thinking that with 12 different fluxes, in all combinations, you've got a choice of 4,095 constellations. But when you realize that we've always just thought we're using one and the same definition in the past, 9 different definitions is quite shocking. The key differences, again, are between the coupled and the offline setup, between transient and equilibrium environmental conditions, and if you perform a reference or not. And because you need a magnifying glass to read all this, I'm just going to pick out 3 very common setups to highlight the differences between them again. So first, we've got the Earth system model setup. And as we said, it includes the land use feedback, because this doesn't cancel in the with and without land use simulation. Now, of course, it's very debatable. If we increase CO2 due to land use emissions, and this feeds back on the pristine rainforest in the Amazon never touched by humans directly, should that be accounted towards the land use emissions, or should it not be? Usually it's not, but some studies did. For example, the one by Aurora and Burr or by Kuhn-Strassmann. And this is very different in the GV2M setup, which prescribes the same climate both times where this flux cancels. And this is probably the most common setup found in literature, which was introduced by Stephen Sitch in the McGuire and our paper. Another difference, the offline GV2M setup, when it's run transiently, is here, accounts for this loss of additional sink capacity, because we see the difference between potential land and managed land. But this doesn't exist when you use equilibrium climate in your simulation setup. And this is, for example, what Elena Shevlyakova published a few years ago. And we see that these differences put in numbers are really major. This table tried to summarize all those studies where the same model is used with different definitions, so that's pretty consistent in itself. And then I give the numbers here that when you include these effects, your net land use flux will change by this number. So for example, when you include the land use feedback, because you have a coupled Earth system model set up, your net land use flux will be 25 to 50% lower as when you exclude the land use feedback. And this is something that 2 models show here. The net land use flux excluding the feedback and then including it. It's only half the original size. The loss of additional sink capacity, when you account for transient environmental changes, it didn't matter all that much historically, but for the future, where we've got strong CO2 fertilization, it may easily double your estimate of the net land use flux. And then if you waive the reference simulation and exclude regrowth and delayed emissions, regrowth and delayed emissions cancelled historically by chance. But the regrowth becomes very important in the future, and your estimate may be increased by a factor of 4 to 10 if you do not include the regrowth. So what are the consequences of this confusion in terminology? There's a kind of fake uncertainty, because it's totally unnecessary to have it in model intercomparison studies. In the recap study, we had 13 different publications used, which applied 4 definitions. In the most recent peer-reviewed estimates of the Global Carbon Project, 5 studies were compiled, but they used 5 totally different definitions. And even in the IPCC scenarios, the 4 integrated assessment models applied 3 different definitions of the net land use flux, but still were harmonized to exactly the same value. This uncertainty propagates to the terrestrial sink because it's derived as a residual term. And then a third consequence, when you use multiple setups to quantify your residual sink and the land use flux, you will inevitably double count or omit certain fluxes and will not be able to close your current balance. So to conclude, we found at least 9 different definitions used in publications of the net land use flux. We've been comparing apples with oranges and really with all kinds of other things. And this explains the spreads in estimates of about 2 to even 4 to 10 for future estimates. We should only compare those estimates that use exactly the same definition. This is a great way to simply reduce the uncertainty range. The question which definition is the right one depends on the scientific question you're answering. You try to answer, but when we do a model intercomparison, we need to agree on one and the same definition, and whenever someone puts out a new estimate of the net land use flux, he or she is strongly encouraged to clearly define which definition they are using. And with this, I thank you very much for your attention.
Thank you, Julia, for this presentation. Maybe you have time for one question. Any